Hi, my name is Barkin Özbek. Today, I'm going to present my research project, which is a deep learning approach for crowd detection in beaches. So let's see our agenda first. Firstly, I'm going to introduce my project and I'm going to describe our aim and objectives. Then I'm going to present my research questions and our methodology. Finally, I'm going to present my solution and discussion with providing future work. As we know that deep learning and machine learning approaches are a recent trend in IT industry. Object detection could be considered as one of the vital tasks for the machine learning approaches. And crowd detection could be also considered a task in object detection that is a big interest that has a big interest from the industry. Different than normal crowds, for this research project, we prefer to go into beach areas. Normally, if you know about the recent crowd detections projects, they are all happening in the streets or in shopping malls or like small areas. With this project, we are trying to capture a big area in the beach and try to identify swimmers, surfers, and the jet skis. Next, our aims and objectives. As I said, our aim for this project is detecting swimmers, surfers, and the jet skis in the sea with using deep learning and machine learning approaches. And with using our detections, we would like to count the swimmers in the seaside as well. And finally, we plan to deploy our model to an application in iOS platforms and detect the crowd with using the camera of the device. Research contains two neural network models. First one is ResNet 152, which is developed from Microsoft research team in 2015. And this model is a winner of ILS VRC 2015 competition in image classification, detection, and localization, and also winner of MS Coco dataset in 2015 in terms of detections and segmentations. So why this model was so successful at that year? Basically, the main idea was solving the problem of vanishing and exploding gradient at that time. Basically, this problem happens when you go deeper in neural networks with adding additional layers to your network. This could be resulted in two ways. As we said, one of them is vanished. Your network could vanish, means your error function becomes zero, and it could gradiently explode, which means your error function gets too high. So this research team find an optimal way to keep your error function in a good way, not zero, not too high. So basically they introduce shortcut connections, the picture you see at the below. The X value comes from older layers and it combines with the new weight layers, which are small values, and then passes the value to the next activation function, which could be ReLU in that time. So this way, they introduce ResNet 18 first, then 32, then 50, 100, and 152, and means that they can go deeper as much as they can. This is a good approach for our project, crowd detection, because we are dealing with really small pixels. Our angles of the data, our angles or proportions are really high, and the swimmers, surfers contains really small pixels in the data. So we believe that ResNet 152 could be a good option to for our research. Next, SST MobileNet is the second one. This is developed by Google in 2017, only for mobile devices. The version 1 contains depth-wise separable convolutions as efficient building blocks. However, they could not get the expected results with this net architecture. A year after the release, in 2018, Google released version 2 for SSD MobileNet, which has linear bottlenecks between the layers and also shortcut connections between the bottlenecks. As the picture below, you can see the architecture, new architecture. We use this model for our application as a prototype. Next, I'm going to talk about our methodology. We can think this project as a whole deep learning project as well. So basically, we divide our methodology into 6 parts. First, dataset preparation. Second, annotations. Third, training the first model, and fourth, training the second model. And we compare them to understand how good we can perform. And then at the end, we develop our prototype. Our dataset preparation. Dataset preparation is a very vital task for machine learning projects. Our supervisor, Dr. Navin Sharma, provides us 25 videos for this task. These videos captured by drones. As you can see, the quality of the videos are very high, which is a really good thing for our annotations as well. Makes our life easier basically. We watch all the videos, noted the crucial parts of the videos, and then extract them as frames, which could be also think as a pictures. The important fact is we need to convert the sizes of the frames as well. Basically, these ones were about 180 to 1920. We decrease this one to 720 and 180. And then we go to the annotations task. Annotations, once we get the data and images, we need to label the objects inside of those images. For this task, our classes are swimmers, surfers, and jet skis. We found a really good repository from GitHub, which is called LabelAMG. As you can see in the picture, there is an illustration of the software. It's very straightforward. You just need to create your rectangles and zoom in and zoom out to swimmers or surfers, and then label them as who they are. Then it creates you the XML file, which is which is the most critical thing for our TF records, which is also TF records is used as an input for model training as well. Next, I'm going to explain our results from first model, which is ResNet 152. We performed 100,000 iterations to get the results. To understand the results, we use mean absolute precision, and these graphs are for results from that. As you can see, the precision and the recall is like identified here. For jet ski, our average precision is 76-77%, which could be considered as a good, and for surfers 66%, and swimmers is 60%. We can think that ResNet 152 could be a good approach, and it's not disappointed us in terms of our results. Here, I will show you a quick video about our results. As you can see, this is a mean absolute precision way. So the greens are the correct detections and the reds are wrong detections from our model. We can see that about 70% it was working really well, and in this way also we can count as well as in the output file. We also able to count the numbers of the detections here, which will give us the how many people were there actually. For the Model 2 SST MobileNet version 2, unfortunately we did not get that good result from this model. As you can see, jet ski percentage was around 13, swimmer percentage was around 30, and the surfer percentage was around 17. We identified that the problem was because of the image sizes. Basically, SST MobileNet we used as a transfer learning method here, and they all was trained with images which has 300 by 300, and our images was at that time really high considering to the 300 by 300. So this was one of the reasons this model wasn't performed really well. But for the prototype, we go into the images again and resize them, and then train again and get the results. Here, next step, I'm gonna show our results and as a prototype, which we developed in iOS mobile application. For this task, we need to create a TF-Lite version of our models, which is also supported by TensorFlow object detection API. Once we generate the TF-Lite version, we could put that the file to our mobile application and try to connect the detections with the camera as well. Here we have two simulated videos from our application. We follow the TensorFlow documentation to generate this application and deploy our model to the application as well. As you can see, we use our dataset to detect the swimmers. Both of the footage has some detections and like they could be confident as well. There are still room for improvements for the application, but for a beginning it could be definitely a case study we could focus on for the future. Thank you for listening me. If you have any questions, I would like to answer it for now. Yes, please.